Welcome to the last video of Unit 15. In today's video, we're going to talk about a change of variables in multiple integrals. So we're looking at double and triple integrals today. So change of variables, we've already done. We took a double integral and we converted it to polar coordinates. We've taken a triple integral and we've converted it to cylindrical and spherical coordinates. And the question today is, what are we going to do if we have some x and y that we want to convert to a different set of coordinates, right? So we have some transformation and then the inverse transformation to take us back. So we have some point and we want to convert from xy to the uv plane or some other variables so that it's easier to integrate. Initially, this isn't going to make much sense, right, until we see an example. So let's first just start by talking about some transformation. So we're going to look at what do we mean by this transformation, and then we'll get into the calculus, the integration part of it. So this example number 1, let's say that t is a transformation that takes us from uv to xy defined by these two equations. The first thing we're doing is we're finding t of 1, 3. So what that means is u is 1 and v is 3. So we're substituting those into the equations above. So for x, we would get 1/4, 1 add 3. So our x would be 1. Likewise, our y would end up being -1. So in the uv plane, the point is 1, 3. In the xy plane, it's 1, -1. Okay, so the next thing that we might want to do is we might want to sketch the image of t that is bounded by -2 to 2 and -2 to 2. So for u and v. If we start by sketching this in the uv plane, our u is going from -2 to 2, and so is our v. So poor figure, but this is the region that we are looking at. And we might call that region S. And we want to know, what is this same region going to be in the xy plane? Okay, so we have some numbers here. And if we just start plugging in some numbers, like we plug in -2 for u and -2 for v, that's only going to give us a point, right? And it's going to give us a point of x comma y. So there's infinitely many points here. That is not going to be particularly helpful to us. So it's not going to be particularly helpful just to plug in random numbers. Instead, our plan is going to be to sketch several u and v curves, u going from -2 to 2, and v going from -2 to 2 also. Now, in order to do that, so we want to sketch those curves. In order to do that, though, we need to know u and v in terms of x and y. And initially, we might not see where this is going, but if you stick with me, I promise that you will. Okay, so we're going to start with these two equations. I'm going to multiply this one by 4 to get rid of the fraction and this one by 2 to get rid of the fraction. So I end up with 4x is equal to u plus v, and I end up with 2y is equal to u subtract v. So the first thing that I want to do is I want to add those. So if I get 4x is equal to u add v and 2y is equal to u subtract v, and I add them, I'm going to get 4x add 2y is equal to 2u, or u is equal to 2x add y. Okay, so the question then is, how is that helpful to us? I'm going to move this over here to the left. So I get u is equal to 2x plus y. Well, now I can go back and say, I have these bounds for u, so let's draw some curves. If I choose u to be -2, that gives me -2 is equal to 2x add y, or the line y equals -2x subtract 2. So that gives me this curve right here for u equals -2. Then maybe I'll decide to do u equals -1. So I get -1 is equal to 2x add y, or y is equal to -2x subtract 1. So it's going to be a similar idea. And I will continue until I'm on the other side of the bound for u equals 2, which gives me the line y equals -2x add 2. Which is that line right there. Okay, so now we're going to have to do the same thing for v. So what I'm going to do is I'm going to take my two equations, and this time I'm going to subtract them. So I get 4x subtract 2y is equal to 2v. So our v then is 2x subtract y. So then I'm going to bring that over here. Our v is 2x subtract y. So again, I'm going to choose some values of v. I might start with -2. So I get -2 is equal to 2x subtract y. So y is equal to 2x add 2. So that would be about this. Sorry, I know I made my graph very small, so hopefully you made yours a little bit bigger. And again, I would keep going, and I'm going to go all the way up to v equals 2. So I would get 2 is equal to 2x subtract y, so y is equal to 2x subtract 2. Which is that line right there. And then of course there's some in the middle. There's v equals -1, -1.5, v equals 0. So there are infinitely many of those lines. And so our image then is this region right here. So what t is doing is it's taking this rectangle here and it's transforming it into this kind of diamond shape. So that is the way that you would go about this process. Now, was that long? Yes. But we're going somewhere with this. So this is not very often what you're going to be doing. Okay, we're not going to be sketching these. We're already going to be given a transformation, or we're going to be taking a transformation. So the logical question is, why are we bothering to do this? And that's what we're going to look at in the next page. The reason that we do that is that sometimes it's easier to integrate in one region than it is in the other. So for example, on that previous page, it would be very difficult to integrate over that diamond. That diamond would have required separate integrals, right? The left and the right bounds were not constant. The top and bottom bounds were not constant. But instead, it would have been significantly easier to integrate in that rectangle, which we called S, or really it was a square. Would have been much easier to integrate over the square than it would have been over R. So that's what we're taking a look at today, is can we take a region that is difficult to integrate over and make it into one that's easier. So that's what we're going to look at now. Before we get into that integration, we need to define something, and it's called the Jacobian. So the Jacobian of x and y with respect to u and v is the following. So we are taking, first of all, this is the notation for the Jacobian. This is the partial of x with respect to u, the partial of x with respect to v, and so on. And then if you remember, these bars indicate the determinant. So we are finding the determinant. We're not finding a matrix. We're using the matrix to find the determinant. And again, the question you should be asking yourself is, why do we care about the Jacobian? Why we care about the Jacobian is it gives us the extra factor when converting our integrals. Now, you've seen this before with some of the conversions that we've done. When we converted a double integral to polar or a triple integral to cylindrical, you added an r. That r was just the Jacobian. That was the Jacobian of taking x and y and converting it to r and theta. When we converted to spherical, this was a triple integral only. You added rho squared sine of phi. Again, that was the Jacobian. So what this gives us then, or what this leads us to, is if we have a double integral, although it's also a triple integral, and we convert to something different, so instead of x and y, we're going to do it in terms of u and v, that du dv gets added, but we also have to put in the Jacobian. And this does not indicate determinant, right? Because our Jacobian is just a factor. This indicates absolute value. So we're going to do the absolute value of the Jacobian. Okay, so let's take a look at some examples. Example 2, first thing we're going to do is we're just finding the Jacobian. So notation-wise, we're looking for the Jacobian of x and y when we convert to r and theta. So this is going to be the partial of x with respect to r, the partial of x with respect to theta, partial of y with respect to r, and partial of y with respect to theta. So partial of x with respect to r is just cosine of theta. Partial of x with respect to theta is going to be negative r sine of theta. Partial of y with respect to r is sine of theta. And then we get r cosine of theta. So now we're doing the determinant. So this gives us r cosine squared of theta, add r sine squared of theta, which is equal to r. Now, that shouldn't be a surprise. You should have already known that that was r. And that's because when we convert to polar, we add that extra r. Okay, let's look at 2 other examples. Okay, so next page, we are evaluating this double integral of 3xy dA, where r is that region. So first thing to review, what is this double integral actually telling us? So this double integral, remember, is going to tell us the volume. It's the volume between r and this surface z equals 3 of xy. Okay, so we're going to start this the way that we normally would, and we're going to draw out this region r. So if we go to draw out r, we have x subtract 2y equals 0. So this is y is equal to 1/2 x. This one is going to give us y equals 1/2 x plus 2. We get y is equal to 4 subtract x, and we get y is equal to 1 subtract x. Okay, so if I go to sketch these then, there is my y equals 1/2 x, 1/2 x plus 2, it's there, 4 minus x, it's just a rough sketch, remember, don't judge it too much, and then 1 subtract x. Okay, so our region R is this region right here. Now, if we were going to set up our double integral, if we integrate with respect to x first, let's say, we're going from this bound to this bound, then all of a sudden the left bound changes and the right bound changes. So if we integrated with respect to x, we would need 2 separate integrals. Similar idea if we integrate with respect to y. We have the top and bottom bounds, but then all of a sudden the top and bottom bounds change. So we would then have to do 2 separate integrals again. Okay, so that is why initially we're going to say we're going to probably do a change of variable. Now, if we look back at these equations we've been given, you notice that x minus 2y comes up twice, and x plus y comes up twice. So that would lead us to the idea that maybe we let u equal x subtract 2y, and we let v equal x add y. So then we know that our u is between 0 and -4, and our v is between 4 and 1. So if we sketched this on the uv plane, u is going to go from 0 to -4, and v is going to go from 1 to 4, so this is now the region we're looking at. So that is a significantly nicer region to integrate over. Okay, so if we're going to do this change of variables, the first thing that we're going to have to do is we are going to have to find the Jacobian. And in order to find the Jacobian, we need x in terms of u and v, and we need y in terms of u and v. Currently, we have u is equal to x subtract 2y, and v is equal to x add y. Okay, so now I'm going to have to solve for either x or y. If I choose to subtract here, that will get rid of my x's. So I get u subtract v is equal to negative 3y. So y then is 1/3 v subtract u. Then if I take those same two equations, I'm going to double the bottom one, so I get 2v is equal to 2x add 2y. Now when I add them, that'll get rid of my y's, so I get u add 2v is equal to 3x. So my x then is 1/3 u add 2v. So remember, the whole reason we were doing this was to find the Jacobian. So I need the Jacobian of xy as it relates to u and v. So if I take the partial with respect to u, I get 1/3. Partial with respect to v is 2/3. So I'm starting with this equation. Now if I look in terms of y, the partial with respect to u is negative 1/3. The partial with respect to v is 1/3. And if I calculate that determinant, it ends up being 1/3. So that was step 1. Step 2 now is change a variable in the integral. So I have the double integral of 3. X is 1/3 u plus 2v. Y is 1/3 v subtract u. I then have the absolute value of the Jacobian, du dv. And we set up here, u goes from -4 to 0, and v goes from 1 to 4. So simplifying a little bit, this gives us 1 to 4, -4 to 0, 1/9 u add 2v, v subtract u, v subtract u, du dv. As we normally do, I'm not going to go through and integrate this because you've done many of those problems already, but I will tell you, if you want to try it on your own, the answer is 164/9. So again, recognize that you want to do a change of variable. You're not going to be told to change variables. You're going to have to recognize that that will make your life easier. You don't need to sketch these, but you do need to find the Jacobian, which starts with find x and y, then the Jacobian, and finally you can get to that integral. Okay, at this point you might be wondering, well, what if we have 3 variables though? What if it's a triple integral? And that is a great question. What if it's triple integral? You can still do this exact same process. So that is the last example that we're going to be looking at, is what if we have a transformation with 3 variables instead of 2, like you see here, rho, phi, and theta. And the question is, what is the Jacobian? What is the Jacobian? So starting with some notation, we're looking at the Jacobian of x, y, z in terms of rho, phi, and theta. And so that's going to be partial of x with respect to rho, partial of x with respect to phi, partial of x with respect to theta, and so on and so forth. So I'm going to get us started. We're using these equations that we have above. So the partial with respect to rho would be sine of phi, cosine of theta. Then the partial of x with respect to phi would be rho, cosine phi, cosine theta. And then the partial with respect to theta is going to be negative rho, sine of phi, sine of theta. At this point, I want you to pause the video and keep going. See if you can get as far as you can. If you think about it, you really should already know what the Jacobian ends up being. So pause the video, try continuing with this matrix and finding the Jacobian. Come back when you're ready to go over it. Okay, going back, there was a typo here. Hopefully you know that that shouldn't have been another x equals. Should have been y equals. Okay, so all the partials of y, we get sine of phi, sine of theta, and then we get rho cosine of phi, sine of theta, and then we get rho sine of phi, cosine of theta. And then once we get down to z, the partial with respect to rho is just cosine of phi. Partial with respect to phi is going to be negative rho sine of phi, and there is no theta, so that partial is 0. Okay, now let's see how good our determinant skills are. So what I'm going to do is I'm going to take this row. So the first element I have is sine of phi cosine of theta, and then I'm going to multiply by the determinant of this matrix, which is 0 add rho squared sine squared phi cosine of theta. Then as I go to this next element, I'm going to switch the sign, so that is rho cosine of phi cosine of theta, and that is now the determinant of the matrix with those 4 components. So again, I get 0, subtract sine of phi cosine of phi cosine of theta, and I forgot there's a rho here. And then lastly, this last element, I have negative rho sine of phi sine of theta multiplied by the determinant of this matrix, which is negative rho sine squared phi sine of theta, subtract rho cosine squared phi sine of theta. Whew. That was a lot, so hopefully I didn't make any mistakes. Now let's do some distributing, some simplifying, all of that good stuff. When I multiply these, I should get rho squared sine cubed phi cosine squared theta. The negative and the negative is going to give me positive rho squared sine of phi cosine squared of phi cosine squared of theta. Okay, so then down to the green, I'm going to get rho squared sine cubed phi sine squared theta. And again, I'm going to get a rho squared sine of phi cosine squared of phi sine squared of theta. Woo-hoo. Okay, doing a little simplifying. We notice we have cosine squared theta adds sine squared of theta. So if we factored this out, it would give us rho squared sine cubed phi. And then we have cosine squared theta adds sine squared theta. So again, this would have been factored out. So that gives us a rho squared sine of phi cosine squared of phi. Okay, doing some factoring. We can factor out a rho squared and a sine of phi, which leaves us with sine squared of phi, add cosine squared of phi, which is 1. So finally that Jacobian is rho squared sine of phi. And again, we already know that we should have known that we were going to get that because these are our spherical coordinates. So these are our spherical coordinates, and we saw in the previous video to this that when we converted from rectangular to spherical, this was our extra integrating factor. So I hope this has been helpful and informative to you. If you have any questions, please, of course, make sure that you ask. This was the end of this unit, so I look forward to seeing you again in Chapter 16.